Hello everyone, my name is Görkem Kaya and alongside my group members, we are thrilled to present our findings on the integration and innovation of discrete element method and finite element method in engineering. Today our focus is to delve into the integration, applications and innovations surrounding DEM and FEM. We aim to demonstrate not just the theoretical aspects but also the practical implications and the latest advancement in these techniques. And here is the presentation of the outline, and let's take a brief look at what we will covering today. And for the introduction part, we will start by introducing the principles behind finite element method and the discrete element method, discussing their importance in the fields of engineering and science. And for the literature review part, we will then move to the review of key scholarly articles and the studies that provide a backdrop to our current understanding and applications of these methods. And for the equation principle section, we will cover the core mathematical principles and equations that underpin both DEM and FEM. And for the simulation case, we will present a case study involving a simulation to give you a clear view of how these methods are applied in the real-world scenarios. And for the application part, we will explore the diverse applications of both methods across different engineering disciplines, highlighting their versatility and their impact. And finally, we will summarize our discussion, draw conclusions from our findings, and offer insights into future directions in this field. Finite element method is a numerical technique used for solving differential equations that describe the physical phenomena in engineering and the applied sciences. It's a powerful tool for simulating and analyzing the behavior of the complex structures and the systems under various loading conditions. And discretization, interpolation, weak formulation, assembly, boundary conditions, solution, and the post-processing are the breakdown of the finite element method. And the FEM is widely used in the various fields of engineering, including structural analysis, heat transfer analysis, fluid mechanics, electromagnetics, and geomechanics. It allows engineers and the scientists to analyze the behavior of the complex systems, optimize design, predict the performance of the engineering structures and the components under different operating conditions. The discrete element method is a computational technique used for predicting the mechanical behavior of materials and the structures composed of discrete, separate components such as grains, stone blocks, and bricks. It's particularly useful for analyzing the behavior of materials like corn in a silo, dry sand, rubble, or structures like monastery arches and old stone bridges. The significance of the DM is that it provides a unique approach to modeling mechanical systems by using on the interactions and the movements of individual elements. This method is essential for understanding the fundamental behavior of systems with a discrete internal structure, with changes in the response to external forces. For instance, the failure of the masonry vault is often determined by the separation or sliding of neighboring layers, a phenomenon that DEM can simulate accurately. And the advantages over the traditional method is the traditional continuum-based calculation techniques such as the finite element method or finite difference methods cannot directly reflect the discrete nature of these materials and the structures. DEM fills this gap by allowing the engineers to model and analyze the behavior of each element in the system, offering insights into phenomena that will be difficult or impossible to study otherwise. The historical context of the DEM is developed began in the 1970s as an engineer sought alternative methods to model the discrete nature of the certain materials and structures. By the 1990s, advancements in the computer hardware made it possible to analyze the realistic problem using DEM on personal computers, marking it as an essential tool for modern engineering challenges. The significance of DEM is very broad. For example, the unique approach, the discrete element method, revolutionized how engineers and the scientists model the mechanical behavior of complex systems. Unlike traditional methods that treat materials as continuous, homogeneous entities, and DM delves into the interactions at the granular level. This microscopic viewpoint opens a new avenues for understanding the dynamics of the system with intricate internal structures. And for the broad applications, the DM versatility extends beyond the traditional civil engineering challenges like touching on fields like pharmaceuticals, where it aids in the tablet formulation process, and mining for analyzing ore flow in chutes and the hoppers. It also plays a crucial role in the geotechnical engineering, aiding in the study of soil behavior, landslide analysis, and the flow of granular materials. In each of these applications, the ability to model individual particles or element yields insights that are critical for safety, efficiency, and innovations. And for the real-world problem solving by accurately simulating the behavior of discrete elements under various conditions. DEM helps predict the outcomes of scenarios that are either too dangerous, expensive, or impractical to test in reality. For example, in the designing of high-capacity silos, DEM simulations can prevent catastrophic failures by identifying the stress points and the flow blockages that might not be evident through traditional analysis methods. And enhancing the understanding of material behavior is one of the features of the DEM, which has significantly contributed to our understanding of material behavior under stress, deforming, and the flow conditions. It has shed light on the phenomena like segregation, mixing, compaction, and the effect of the practical shape and the size distribution on the mechanical properties of the materials. This detailed understanding is invaluable in designing more efficient and reliable materials and structures. And DEM can lead innovative engineering solutions by allowing engineers to visualize the macroscopic interactions within a system. DEM paves the way for innovative solutions to long-standing problems. For example, in the case of a Montessori vault failure, DEM simulations can help in designing the reinforcement that specifically target the weakness in the structure's discrete elements, leading to more targeted and cost-effective interventions. And finally, the computational advances of the DEM is started with the evolution of DEM has closely parallel advancements in the computational technology, enabling the analysis of increasing the complex systems within the reasonable time frames. Today, high-performance computing and cloud technologies are expanding the boundaries of what can be modeled, bringing us closer to the future where virtual testing can complement or even replace the physical prototypes for a wide range of engineering applications. The advantages of DEM over traditional methods are the micro-level insights. Unlike the continuum-based methods that approximate materials as a continuous media, DEM models the individual particles or elements, offering a granular level of insight. And this allows for an accurate representation of the behavior of materials like granular soils, powdered chemicals, or composite materials, where the interaction between individual particles significantly influences the overall mechanical properties. Handling nonlinear dynamics, another advantages of the DEM, which excels in scenarios involving large deformations, nonlinear material behavior, and the complex boundary interactions, which are challenging for traditional finite element analysis and finite difference methods. By explicitly simulating the contacts and the forces between discrete elements, DEM can accurately predict outcomes in the processes such as mixing, compaction, and the flow of granular materials under varying load conditions. Adaptability to complex geometries, the system with irregular shapes and heterogeneous compositions pose significant challenges for continuum-based methods due to the difficulty in the meshing and the need for simplifying assumptions. And the DEM's particle-based nature inherently accommodates complex geometries, enabling the analysis of systems ranging from fractured rock masses to regular shape pharmacology tablets without the need for geometric simplification. And the dynamic contacts and the separation analysis is another traditional method. It analyzes another advantage over the traditional methods because the traditional methods often struggle with the situations where components separate or come into contact dynamically, such as in the case of rock falls, machinery involving bulk materials, or the structural analysis of buildings during earthquakes. DEM inherently tracks each element's positions and can dynamically update contacts, making it uniquely suited for studying phenomena involving separation, collision, and the dynamic reconfiguration. And enhanced predictive capabilities is another advantage of the DEM, because by providing a more accurate representation of physical systems, DEM enhanced predictive capabilities, reducing the need for expensive experimental testing. This not only saves the time and resources, but it also facilitates the exploration of a broader design space, leading to optimized solutions and innovative designs. The integration of discrete element method and the finite element method modeling techniques is a relatively recent development in computational mechanics. Here are some historical steps in the integration of the DEM and the FEM modeling. The discrete element method is originated in 1970s and primarily in the field of granular mechanics. Researchers such as Peter Condell and Oreste Strag were among the pioneers who developed DEM to model the behavior of granular materials. And throughout the 1980s and the 1990s, DEM found application in various industries, including the mining, pharmaceuticals, and the civil engineering. Researchers continue to refine DEM algorithm and expand its capabilities to model complex systems. Concurrently, finite element method continued to evolve with ongoing development in numerical techniques, element formulations, and the software capabilities. FEM became a widely used tool for simulating the behavior of structural and the materials. And in the late of 1990s, researchers began exploring the integration of the DEM and FEM for problems involving coupled solid fluid interactions and the soil structure interactions. Initial attempts focused on developing interface modeling to exchange forces and the displacement between the two methods. The early 20s saw a surge in interest in the multi-scale modeling approaches, including the coupling of DEM and the FEM. Researchers recognized the need for more comprehensive understanding of complex systems that exhibit behavior at multiple length and the time scales. And over the past 2 decades, significant progress has been made in developing coupling techniques to integrate DEM and FEM models effectively. Various strategies have been explored, including explicit coupling, implicit coupling, and the hybrid approaches. And the availability of high-performance computing resources and the advancements in software tools have facilitated the integration of the DEM and the FEM modeling. Commercial and open source software platforms now offer capabilities for coupled DEM and the FEM simulations. And applications in geotechnical engineering and beyond from 20s to present, integrated DEM and FEM models have found applications in geotechnical engineering, civil engineering, biomechanics, and material science, among the other fields. These models are used to study phenomena such as soil structure interaction, granular flow, fracture mechanics, and the practical fluid interactions. And ongoing research and development today's research in the integration of the DEM and the FEM modeling techniques continues to advance with ongoing efforts to improve accuracy, efficiency, and applicability to a wider range of problems. Challenges such as computational cost, numerical stability, and validation remain areas of active investigation. Expanding franchise of DEM through integration and innovation with the integration with machine learning, the synergy between DEM and the ML is poised to revolutionize predictive modeling in the material science and engineering. Machine learning algorithms can analyze vast datasets generated from DEM simulations to identify patterns and insights that will be impractical for human analysts to discern. This integration could lead to the development of predictive models that adapt and improve over time, enhancing to our ability to forecast material behavior under previously untested conditions. For instance, machine learning could predict the outcomes of adding a new material to a composite or the impact of environmental changes on soil stability with unprecedented accuracy. Enhanced virtual reality experience DM's integration with VR technology promises to transform how engineers and researchers interact with their models. Imagine walking through a virtual construction site, observing the granular behavior of the soil underfoot in the real time, or exploring the internal structure of a tablet during the compression process. These immersive VR experiences will not only aid in design and analysis, but also in education and training, providing an engaging platform for learning about complex physical phenomena. And the advancement material design, the feature of the DEM includes the pioneering design of new materials at the molecular or even atomic level. By simulating interactions at these fundamental levels, researchers can design materials with specific properties tailored to unique applications, such as ultrasound composites for aerospace or highly efficient catalysts for energy conversions. Solving environmental challenges is set to play a crucial role in addressing environmental challenges, from predicting and mitigating the impacts of natural disasters like landslides and earthquakes to optimize the design of renewable energy systems such as wind turbines and solar panels. The ability to model complex environmental systems in detail will be invaluable in developing strategies to adapt to and mitigate the effects of climate change. Interdisciplinary applications of the integration of DEM with other scientific disciplines opens new avenues for research and innovations. In medical field, for example, DEM could simulate the behavior of cellular structures under various stimuli, leading to breakthrough in medical treatments. In agriculture, DEM could optimize soil management practices, enhancing crop yields and sustainability. Collaborative and distributed computing. As cloud computing and distributed computing evolve, DEM simulations will become more collaborative and accessible, enabling researchers across the globe to work together on large-scale models. This collaborative approach will accelerate innovation and allow for the tackling of global challenges through shared computational resources and expertise.
Hi everyone, this is Mrs. Said and I'll be taking you through general principles. Numerical simulations are an indispensable part of engineering and science development. They offer a powerful and versatile tool for exploring, analyzing, and understanding complex phenomena that are often impractical, expensive, or impossible to study through experimental means alone. For example, many real-world phenomena involve intricate interactions between multiple variables and parameters. Through numerical solutions, researchers and engineers can model and analyze these complex systems in a controlled environment, enabling a deeper understanding of their behavior and performances. DEM and FEM are leading techniques for numerical solution for most engineering problems of solid phase. Whereas both methods have unique applications, they're sometimes coupled beneficially to harness their strengths in numerical modeling. The FEM is mostly utilized for modeling continuum media, while the discrete element method is utilized for discrete. The discrete element method, also termed as discrete particle method, is used to simulate granular materials. It determines the motion of individual particles by exerting forces and torques stemming from either external body forces or particle-to-particle interactions. However, DEM as a modeling technique is inefficient for simulating huge quantities of granulated materials. Additionally, DEM assumes that an external object interacting with particles are rigid and immobile, which is not always the case. To overcome these drawbacks, FEM is utilized to model the description of the external continuum of external bodies under the impact of particles. FEM is derived from continuum theory and is utilized for describing deformable continuum bodies. This is particularly important because particles' interaction with deformable structures can strongly influence the rheological qualities of the granular bulk, which is important for industrial applications. So, in this section, we are going to see the reason as to why we couple DEM and FEM. One, to begin off, it is important in multiscale modeling. So coupling DEM and FEM allows for multiscale modeling where the macroscopic behavior of a structure or material can be analyzed alongside the behavior of individual particles or components. This approach is beneficial for studying systems that exhibit both continuum and discrete characteristics, such as in the case of composite materials, soil structure interactions, and granular flow in structural foundations. Secondly, coupling of DEM and FEM enables us to model hybrid materials. Some materials exhibit behavior that cannot be accurately captured by either FEM or DEM alone. So coupling these two techniques allow us to model the hybrid materials such as composites or reinforced structures where the continuum behaviors of the matrix is coupled with the discrete behavior of the reinforcing particles or fibers. Thirdly, it helps us improve accuracy in modeling. By coupling DEM and FEM, engineers can achieve higher accuracy in simulation by capturing both the macroscopic and microscopic aspect of a system. For example, in geotechnical engineering, coupling FEM for analyzing soil structure interaction with DEM for simulating granular soil behavior can provide more realistic predictions of foundation settlement and bearing capacity. Number four, it helps us understand complex phenomena. So, coupling DEM and FEM facilitates the investigation of complex phenomena and involve interaction between continuum and discrete domains. For instance, in pharmaceutical manufacturing, coupling FEM for fluid dynamics with DEM for tablet compression can help us improve understanding of the compaction process and tablet quality. Lastly, it is actually very important in optimization and design process because it helps us understand how stresses can be distributed in such complex media. So the coupled DEM and FEM technique applies to various types of challenges that require various strategies. And therefore, we're going to look at the four major types of classifications, which include one, the surface coupling. Surface coupling is used for simulating granular media which interacts with solid structures as shown in Figure A. In this case, DEM is used to simulate the granular media while FEM is used to simulate the FEM continuum domain. An example of this includes a ballast-slipper interaction whereby DEM is used to simulate the ballast while FEM is used to simulate the slipper. This technique facilitates the accurate modeling of a system where both continuum and discrete behavior coexist, such as soil structures interaction, granular flow, and particle fluid interactions. At the interface between the FEM and DEM domains, contact detection algorithms identify interactions, while forces and displacements are transferred between the continuum elements and discrete particles to simulate realistic interactions. Through interpolation and averaging techniques, quantities such as stresses and displacements are exchanged between the two domains to ensure compatibility and continuity. The second type is known as volume coupling, and this technique is used to simulate granular domain within a solid domain such as a fracture in a solid medium. In this case, DEM is used to simulate microstructure near the fracture, while FEM is used to model intact parts. For example, considering a brick wall that can break, FEM is used to simulate the wall, while DEM is used to simulate bricks near the fracture zone. Through iterative data exchange algorithms and possibly mesh adaptation techniques, volume coupling enables the simulation of coupled physics phenomena across the interface, allowing for accurate representation of complex interaction between solid structures and granular material. This technique finds application in various engineering fields, including civil, mining, pharmaceutical, and material science. Fourthly, we have multiscale coupling. And this technique is used in cases where the granular media have properties like a continuum. An example of this is a box of sand consisting of millions of particles which can be considered as a continuum on a large scale. In such a case, focusing on an individual sun grain from a microscale perspective, the individual behavior is visible. Therefore, FEM is used to model the macroscale behavior of the medium and DEM for modeling the microscale, representing a detailed model of the macroscale. By combining FEM and DEM, excuse me, engineers can simulate the macroscopic response of a structure or material while simultaneously capturing the detailed interaction between individual particles or components. This approach provides a comprehensive understanding of the system's behavior, allowing for more accurate predictions and insightful analysis of phenomena that involve both continuum and discrete characteristics. Multiscale coupling of FEM and DEM is particularly valuable for studying multiscale phenomena in various fields, including civil, pharmaceuticals, material sciences, and biomechanics, where the interaction between the different length scales plays a very crucial role in the overall system behavior and performances. Fourthly, we have contact coupling. This is basically a pure FEM approach utilizing contact detection like DEM. An example is shot pinning, whereby an object is shot on another object. Interaction physics becomes only relevant as soon as one hits the other, leading to contact. The contact coupling mechanism enables the exchange of forces and displacement between the FEM and DEM domains at their interfaces, allowing for accurate representation of contact interactions, deformations, and failure mechanism. By seamlessly integrating FEM and DEM, engineers can analyze complex systems where both continuum and discrete behaviors play significant roles, such as soil structure interaction, rock fragmentation, or particle-laden fluid flow, leading to a more realistic and comprehensive simulation for a wide range of engineering applications. So now we will look at the process of coupling DEM and FEM. To begin with, we have to define the problem. And in this initial step, the engineering problem or physical phenomenon being studied is well defined. This involves specifying the materials, boundary conditions, geometric configuration, and any other relevant parameters necessary for simulation. Secondly, we generate the mesh. Mesh generation involves discretizing the computational domain into finite elements for FEM and discrete elements for DEM. This step ensures that the geometry of the problem is accurately represented in the numerical model. Thirdly, we involve the numerical solvers. Both FEM and DEM require numerical solvers to solve the governing equations of motion for the respective domains. For FEM, this typically involves solving systems of linear equations derived from the equilibrium equations using techniques such as the finite element method. For DEM, particles dynamic equations are solved using algorithms that simulate particle motion and interactions. Fourthly, we undertake coupling interface. So the coupling interface establishes communication between the FEM and DEM solvers, allowing them to exchange information such as forces, displacement, and boundary conditions at the interface between the continuum and discrete domains. And then we do time integration, which is a process of advancing the simulation in time to capture the dynamic behavior of the system. Both FEM and DEM simulation are advanced in time using numerical integration schemes such as explicit or implicit time-stepping methods. Thereafter, we couple algorithm. Coupling algorithm determines how information is exchanged between the FEM and DEM domains at each step. This may involve transferring forces and displacement between mesh nodes and particle contacts, ensuring compatibility and continuity of solution across the interface. 7. We perform contact detection. Contact detection is a critical aspect of DEM-FEM coupling as it identifies and resolves interaction between particles and mesh elements. 8. We undertake solver execution. Once coupling interface, time integration, coupling algorithms, and contact detection are established, the solver for both FEM and DEM are executed to advance simulation in time. The solvers iteratively solve the governing equation until convergence is achieved for each time step. 9. We perform post-processing. Post-processing involves analyzing and visualizing the simulation results to extract meaningful insights and draw conclusions. This may include generating plots, animations, and quantitative data to evaluate the behavior of the system, assess performances, and validate the numerical model against experimental or theoretical data. I will pass over to my colleagues who will explain further about coupling of DEM and FEM. Thank you.
I'm going to discuss some of the governing equations of FEMDEM model, which is used to simulate the mechanical behavior of geomaterials. In the model, geomaterials are represented as discrete spherical particles that are bounded at the contact points, while the surrounding domain is simulated using finite elements. I will illustrate three main formulations. First, the interaction between particles over balls, then the equations of motion governing these particles, and finally, the interactions between the particles and the walls. Consider that we have two balls, P and Q, colliding at the contact point C. A unit vector n which connects the centers of the ball is defined. The components of the unit vector n can be expressed by the following equation. Ni is the components of the unit vector n, and SIQ, SIP are the components of the position vectors of the centers of the balls. Additionally, the overlap is described by this equation here. R is just a radius of the balls. Thus, the coordinate of the contact point C is expressed as this equation here. And finally, the contact force F, which is crucial to our formulations, can be resolved into normal and shear force. In the numerical simulations, the shear force is updated at each time step, considering two main factors. First, we consider the rotation of the contact plane. Here, the initial shear contact force is rotated around the intersection line of the old and the new contact planes. Next, the rotation of the two balls around the factor n is considered. The final shear force is then determined using the following equations, where the average omega is the average of the angular velocity of the two balls around the new factor contact normal factor, which is equated as here. Furthermore, the relative velocity factor of the balls at the contact point C is shown here, where x dot CQ is the velocity factor of the contact point C of the ball, and which it can be formulated as S dot Q plus the omega Q cross product the C minus SQ, where the SQ is the velocity factor of the center of the ball Q, and the XC is the position factor of the contact point. The relative velocity factor can be decomposed into normal and shear components of the contact surface illustrated here. And the following equation shows the increment of the relative normal and shear displacement component during each time step. To further elaborate on how interactions at the contact point is simulated, a contact bound model is utilized. So the model is depicted in this figure, where the mu is just a friction coefficient, SB is the shear bond, NB is a normal bond, Ks is shear spring constant, and Kn is normal spring constant. So at the contact point, the behavior is primarily elastic unless the tensile normal forces and the shear forces exceed bond stresses for normal and shear stresses. Consequently, the increment of contact point and shear force components are updated as follows. Furthermore, the overall contact shear forces are updated as follows. The use of the colon equals sign here indicates the result on the right-hand side is calculated and then assigned to the parameter on the left-hand side. If the incremental contact point constitutive law is not applied to determine how materials react under contact, then the normal force can be calculated using this equation. As indicated earlier, two conditions must be verified: the tensile of normal forces and the shear forces should not exceed the bound strengths for normal and shear stresses. If they do exceed these strengths, the bonds are considered broken and setting their values to 0, and the contact permanently loses bonding capability. Conversely, if a normal contact force is compressive, then the normal force remains unchanged, and the shear force is equality as using column frictional behaviors here shown. Moreover, the resultant forces and the moments transferred from the contact point C to the center of the balls Q, P, and Q are described by the following equation. To incorporate the motion of the balls, we use central difference method to update the velocity components of the balls. The new velocity components are computed by the following equations, where the m is the mass and the I is the inertia. Finally, in the case of ball-wall interactions, the contact force R is transferred to the nodal points of the tetrahedral wall elements M and ST. And by the way, for the A, the figure in the A, is the line here is the plane of the wall after the ball hits. The relationship between the velocity vector v at any point within the tetrahedron element and the nodal point velocity vector is described by the following equations. Where so v, as is indicated, is a velocity vector. This sign is the nodal point velocity vector, and this side is the shape function matrix, and they are described in these equations here. Ultimately, the equivalent nodal force vector F is expressed using matrix product of the transpose of the shape function matrix and the contact force R.
Now let me introduce the under calculation and the simulation case of the coupled methods between FEM and DM. Based on the equation above, we will only focus on the surface coupling case because it's the more basic and simple one to perform. And for hand calculations, this is a very complicated process between two methods. I can't give a very detailed process, but I can clarify the whole principle and the process of the calculation process. So firstly, let me assume a case there is a ball will impact on a wall with a speed of 8 meters per second, and it will cause influence on the wall. This is a very simple and classical FEMDM question. And based on the equation above introduced by Bruce, we can firstly regard this question as a ball and ball interaction. It means we can extract a unit of the wall and regard this unit as a wall and make a very normal process to calculate the normal force and the shear force between the unit and the wall on the contact point. And after we acquire the contact force R between the unit and the wall, we can calculate the nodal force vector on the unit based on the principle of virtual work. And in the equation on the right downside, phi is the shape function. It depends on the specific question to calculate the nodal force vector. And next is we can regard the FEMDM question as a pure finite element method. So the case will transform to the very simple case, just like the picture on the left side. There is a force which comes from ball impact. And this is a very classical FEM question. First, let me give some material properties of this question. Young modulus, Poisson ratio, and some very simple coordinate point of the 4 points of this unit. So we need to calculate, we not only need to calculate the nodal force, we also need to know the stiffness matrix to calculate the force and the displacement of these 4 nodes. So basically, we need to know the shape function. And just like the picture on the right side, we know the shape function in these 4 points are very simple, based on a new coordinate system, and based on some very basic finite element method. We can also acquire the relationship between a small coordinate system, and the whole coordinate system, which can give us a relationship between stiffness matrix and we need first to know the string relationship between 2 coordinate systems, which is what we need to know the matrix B. This is related to the shape function. And once we know the matrix B, we also need the elastic matrix. It's a very basic three-dimensional elastic matrix for a very simple unit. And after that, we can use the equation, the integral, the string relationship matrix, elastic matrix, and B to acquire the stiffness matrix. After we acquire the stiffness matrix, we can use the matrix relationship, stiffness multiply displacement equals to force. So based on that case, we can now force of the 4 points and the displacement of the points that was impacted by the ball. So stiffness matrix is on the right upper side, and finally we can acquire anything we need, for example, displacement and some force on 3 points. And this is a very simple hand calculation, since it's a combination method between FEM and DM. It's hard to give a very detailed process, but I will work on more about that. And for simulation case, I create a case which also a ball impact walls question. And I used the 2 open source software to finish this case. For DM model, the tool it's Yard open source software. And for finite element method part, I use the OOFEM open source code. It's very, and I also use the Python and Parallel to relate these 2 parts and give a post-processing picture. And in this case, I assume the wall is has a dimension of 1 millimeter, 3 meter, and 5 meter. And the grace density was shown on the picture, and the radius of particles is 0.12 meter. It's a random value. I just give a random value about this the size of wall and particles. And the materials is also based on some common material. I give Young's modulus, density, and the Poisson rates. And for this case, the steps is per step 0.005 seconds and the total 300 steps. Initial condition, I also give a particle motion speed of 8 meters per second. And the boundary condition for the wall is, the bottom of the wall was fixed, but other places are free. So based on these two open source software, I made this simulation, just like this video. The color on the wall means the stress tensor, and we can see the influence of each other. They influence each other.
Hello, I'll be talking about the example applications. I'm Ji-Hoon Bae. So from previous years that I looked at, they were talking about multiple examples at a shallow depth, but I was wanting to go more into a single topic that uses FEMDM coupled model. So the example that I found was the development of an FEMDM coupled model to investigate preliminary compaction of asphalt pavements. So the variation in pavement density is important as the compaction of pavement is so critical to its long-term performance quality. Laboratory tests are simpler to produce, but less accurate. For field testing, destructive drilled samples are used, to which limits on its ability to access density information at specific areas. Coupled FEMDM methods can stimulate and evaluate the characteristics of both macroscopic and microscopic scales. The study that I found was done to investigate the impact of the asphalt mixtures gradation using two mixtures, AC11, which is a dense graded asphalt mixture, and PA11, gap graded asphalt mixture. Different pavement speeds were also used to study the effects of the paving speeds on the compaction process. For the introduction, asphalt pavement compaction is an essential step in the asphalt road construction, affecting the strength and stability of the asphalt mixture, which serves as the service quality and service life. Field compaction process can be divided into three parts. Preliminary compaction, which is a direct influence on the asphalt pavement, which uses the asphalt mix paver to lay out the asphalt mixture according to specifications within the certain width and thickness uniformity. And there's also a repeated compaction and final compaction. Factors that could influence the compaction process is either one, properties of the mixture composition that I said, like AC11 and PA11, environmental conditions, and third, compaction methods. The angularity and size and hardness, if they increase, then the compactive effort also increases. Compaction is defined as gaps between the particle as they shrink. The air between the asphalt particles is continually removed. For the existing investigation, they include the traditional testing or imaging. For example, there's a X-ray computerized tomography, which is also called a CT. They analyze the interior of macroscopic characteristics of rock samples, and they also serve as the auxiliary tool for microscale petrography. The second is the nuclear and non-nuclear gauges, which is also called a density gauges. Nuclear gauges needed to have a license to operate the instrument, but non-nuclear gauges won over because of their user-friendly approach, speed, robust reproductivity, and ease of license. For the last part, ground penetrating radar, which is also called a GPR, it's a non-destructive testing tool that employs radar pulses to detect and picture conditions beneath the ground surface. It is high speed, uninterrupted, and richness of the pavement information regarded as one of the most promising tools. but the application of GPR to forecast the in-place density of asphalt mixture is still in its early stage. Both laboratory and field tests have limitations. Data from laboratory experience often deviate from the field tests. Coring process can also offer precise information, but its irreversibility and risk inflicting harm to the pavement might reduce service life. Additionally, drilling of sample is done after compaction process, so we can't really look at it during the process. To optimize the intervention timing, the compaction monitor or simulation has been done in real life changes in the pavement conditions. Recently, there has been a number of computational assisted methods such as analytical methods, continuum-based methods FEM, and discontinued-based methods DEM. These methods overcome the limitation of traditional research methods and are repeatable and stable stimulation methods. To name a few, Liu used the mechanical response of asphalt mixtures compacted by various rays in FEM. Experiments, digital imaging processing techniques, and FEM were used to compare and evaluate specimens produced using various compaction methods like field compaction, HN compaction, and Marshall compaction. To name another one, Chen used an open source DEM program to construct virtual digital specimen to explore the influence of compaction variables on air void distribution. There are multiple examples that I can name, but because of the time, I'll go ahead and skip that. The coupled FEMDEM approaches are considered to improve the problems associated with the use of either methods alone. One method of the FEMDEM method is that the discrete elements are separated into independent finite element meshes, which considers each discrete element as a deformable continuum and separates them according to their existing discontinuity surface. In order to monitor the interaction between the material and the paving equipment, a modeling methodology was developed in the study through a coupled FEMDEM method. The general purpose of FE software, ABAQUS, I think it's pronounced as Abacus, was used for the modeling. FEM was used in larger areas of the simulation, in this case the pavement base and the paver, and the DEM in smaller, more localized areas. Here was the asphalt mixture component. In particular, each DEM particle representing an aggregate in the preliminary compaction was modeled with a single node element. For the modeling of coupled methods, overview of Abacus for preliminary compaction modeling is as you see here. So we'll start from the start. Setting of the size and shape, property setting for the material properties, assembly determination of the relative position of each part, like the paver, setting of phase duration, output type, output frequency. Interaction was to define the type of contact and related parameters, setting of the type of the load and related parameters, and determination of the mesh model for the topology. As you see, does the model run smoothly and give reasonable results? If it's no, you have to modify the input files. If yes, complete the simulation, output, and analyze the data. One of the key parts of the compaction model is the aggregates, which were generated by the particle generator in Abacus. The particle generator enables a modeling technique in which the DEM is checked only when the particle reaches a defined area, which simplifies the construction of the model while improving the computational efficiency. The particles are released in a direction perpendicular to the inlet surface of the particle generator, and the flow rate should be determined according to this pavement speed. In the study, only one particle generator was used. In order to improve the computational efficiency, the morphology of the aggregates were simplified to spheres, which cannot fully stimulate the aggregate interlocking happening during compaction, because they're not going to be spheres all around. So in this study, the other parts, including the base and the paver, were created and discretized by FEM. The base that was ready to be compacted on the paver was simplified to a shell 3.42 meters wide and 17.14 meters long without thickness, on which two shells 1.4 meters high and around 1.14 meter apart were created as a fence to designate the paver's work path. As a result, of the impact of vibration paver vibration, the unit line pressure is greatly improved. And when the vibration paver continues to make rapid impact on the surface, the same frequency of the pressure waves penetrates into the material layer, causing the material particles to move. As you can see, the paver was placed on the far right side of the base and secreted to the left in the forward direction. The tamper and the part generation were placed in the middle of the specified route. The distance between the lowest part of the tamper and the screed and the base was set at 0.4 meter, which was the thickness of the asphalt mixture initially required to be paved. In front of the paver, the particle generator served as both a unloading truck and the paver blades. The particle generation has almost the same width as the paver body, ensuring that the particles are equally distributed over the road to be paved. So for the results, the asphalt mixture AC11 underwent obvious changes after the initial compact by the paver, which can be seen in this figure. The air voids between the asphalt particles became narrower, while the surface of the asphalt layer became smoother, particularly in step 1, where it was initiated when the paver started moving forward and the particle generator started releasing particles, which lasted for about 2 seconds. Then it went to step 2, which lasted for 1 second, and during which the required number of particles had been fully released. Finally, in step 3, in order to absorb the state of the asphalt layer after being acted upon by the paver still needed to be moved. They needed to move forward at a constant speed until a certain part of the fully acted upon particles was expelled. So in order to access the interaction between asphalt particles and pavers, the relative rotational pattern of particles was chosen to evaluate because it strongly relates to the density fluctuation of the mixture. The preliminary compaction could be accomplished by pressing or compacting particles while their aggregates are continuously rotating and rearranging until the particles reach a stable state. And thus, the degree of compaction can be determined by observing the relative rotational behavior of the particles. So this is an effect of the gradation of asphalt mixtures on the paving process. As you can see, there's A and B. This is the A is the AC11 and B is the PA11. There are a variety of factors that can influence the compaction properties of asphalt mixtures, including, as I said, grading, temperature, like the content, aggregate qualities, and compaction procedures, and other variables. But as I said, in order to examine the influence of gradation on the compaction characteristic of asphalt mixtures, we used AC11 and PA11, which is both with a maximum particle size 11.2 millimeters. 10 particles that would be impacted by the paver in step 2, described in the last section, were chosen. Their rotating motions during compaction were observed, and the angular velocities of their rotational axes in 3 directions, X, Y, and Z, were observed. The one that you're seeing right now is an overview of the rotational angular velocities. And this demonstrates the combined angular velocities of the asphalt particles of the 2 gradation in all directions. The combined angular velocity is defined as the root of the sum of the squares of angular velocities in 3 directions. It can be clearly seen that the particles of AC11, which is figure A, gradations are more active, as some of them even reach the maximum rotational angular velocities of 0.4. While the particles of PA11 gradation generally move more slowly with the rotational angular velocity within 0.25. This example is the angular velocity with paving speed. The asphalt aggregate seemed very active when the paving speed was set to 4 meters per minute. So the one that you're seeing, there's 3 here. The first one was the 4 meter per minute. The second one was 5 meter per minute. The last one that you're seeing right now is 6 meter per minute. For 4 meter per minute with angular velocities oscillating between minus 0.4 to 0.4 as indicated in the preceding subsection, when the speed was raised to 5 meter per minute while the other parameters remained constant, the angular velocity of the aspirated aggregates fell in all directions, with a maximum peak of 0.3, indicating that the compaction was not as good as when the speed was at 4 meters per minute. When the speed was raised again to 6 meter per minute, as you're seeing right now, the activity of the aspirated aggregates were relatively weak, with the angular velocity floating between minus 0.1 to 0.2. The data generated with paving speed as a variable compared to the other, a similar pattern was found that if the paving speed is faster while keeping the other conditions constant, the asphalt mixture will compact less during the preliminary compaction stage. As preliminary research on the FEMDem coupled methods for simulating the compaction, the data obtained from the model may differ from the actual situation for several possible reasons. For example, in this model, the asphalt mixture was only compacted one time under the action of the paver, while it was better to have more than 2 times in real situation. Thus, the compaction has not yet reached the required level. Another limitation could be that the actual aggregates are not represented in the Abacus program, but are instead uniformly substituted by spheres, which decreases the degree to which the simulation is accurate in comparison to the real scenario to some extent. For future research directions, more parameters could be used to evaluate the compaction could be presented. For example, the porosity of the material or the apparent density and the evenness of the pavement. The ultimate research could be that to develop a mature numerical model for simulating the compaction process, which can be applied in building information modeling or road construction and maintenance. Thank you so much for listening.